Welcome to Unit 5, Lesson 12, the number E. Let's learn about the number E. Okay, so let's match the situation with the equation. These equations are going to go with the next four samples. I couldn't put them all on the same page, so we're just going to read the situation and write the answer. A scientist begins an experiment with 400 bacteria, so 400 is our base. The population doubles, our growth rate is 2 every 10 hours. But we're looking at 1 hour. So if we want 1 hour, it would have to be T over 10. And 10 hours, it would double. So which one is that? K. Because remember, 0.1 equals 1/10. 1/10 is 1/10. Okay, an erosion model begins with 400 kilograms of sand. It decreases by 25%. So if we do 100% minus 25%, that gives us 75%. We do not put percentages into the calculator, into exponential equations. Our growth rate is 0.75 because it decreases by 25, but we measure what's left every 10 days, and we want T days. So that's T over 10 again. And from the previous page, that was H. Okay, looking at the next one. The half-life of radioactive element is 10 years. 400 grams, again, is our start. We know the thing is half-life because it's at half. We want T years, again. T over 10, again. And from the previous page, this was F. Okay, in a lake, the population of species of fish is 400. It's expected to grow 25%, so plus 25%. But 400 represents 100%. So you have to add these together to get 125. Then you divide it by 100 because percent, per means divide, cent means 100. You get 1.25. In the next decade, that's 10 years. And T years, that's T over 10 again, which is G from the previous page. Okay, a spot of mold is found on a basement wall. Its area is about 10 square centimeters. Here are three representations of a function that models how the mold is growing. Now, we haven't seen this one before. This is E. E is an irrational number. It is approximately 2.718. And I should probably take this out to 4 decimals. 2.7183. This is an irrational number. It is some scientists or mathematicians' number. It is a number that occurs with certain natural occurring things. And this is the number we're going to start working with is E. It's on your calculator. It's next to the 4. You'll see ln, which is the natural log base E. And E is an irrational number that we're going to use for certain things. Okay. So this graph is probably based on E2. So what do you notice? What do you wonder? This is just three representations. So in Algebra 1, you had an equation, a graph, and a table of values. And they all represent the same functions 3 different ways. And then you also had a story or a situation. So there are 4 ways to represent a linear function or any type of function. There are 4 ways. You use an equation, a story or a situation, a graph, and a table. And if you check the data, it should be close. At 1, it's about 10. You can't really tell. You would probably guess that it was 30 or 40. At 1, it's at 27. Oh, 0 is at 10. 1 is at 27. 3, 2, it's at 74. and then 3 is at 200 or just above 200. So the table and the graph have to match. Okay, here's some functions for each description. For each function described. Now we're going to graph these. So we're going to put these in a y equals. I'm sorry about that. We're going to put these into y equals and see what we get out. Now, when we hit y equals 1 caret x, 1 caret, which is over the division symbol, xt theta n, hit graph, you're going to see a horizontal line, which tells you that 1 is a constant function. It's not actually exponential, even though it is written in exponential form. Because the output always stays the same, it doesn't curve up on one side. This is not really an exponential function. Now, negative x. What negative x will do is go down from left to right when you graph it, when you hit those buttons. So let's draw the graph for this one. If this is x and this is y, then 1 to the x looks like that. Negative x will look like that at a negative 45-degree angle, or 315-degree angle. 1 over x will look like this. This is a reciprocal or an inverse function. And you're going to graph it. Looks like that. And basically what we're doing for these graphs is describing the end behavior. So for A, when x grows very large, y stays 1. For B, when x grows very large, y goes to negative infinity. When x goes very small or to the left, y goes to positive infinity. Now that's coming back. Now, with D, you have to explain what's going on both sides of the graph. When x is positive, as x approaches 0 from the right, as the x approaches 0 from the right should be over there, y goes to 0. No, I'm sorry, positive infinity. As x goes to positive infinity, y goes to 0. Okay, now on the left, it does the opposite thing. So as x goes to negative infinity, y goes to 0. And we've seen this in unit 3, that's coming back. As x goes to 0 from the left, y goes to negative infinity. And once you put this on a graph, you'll see it. So please graph it using the instructions I gave you in the first one. Now, looking at the graph of this function, this does something really goofy. So what happens here is, as it goes to 0, it looks like it approaches 1. And then it looks like it curls up and then comes back down. So it looks something like that. At 0, there's an error. There's nothing on the negative side until you get to negative 0.04. And there's lots of errors on the negative side. So this graph is really goofy. So I had to go past 1. I had to go down into the decimal points. That does something weird. Okay, so now with this graph, with G, you get this going on. On the left side, you get this. On the right side, you get this. So there is a hole in the graph, and it does something different on each side. That's kind of weird. Now, with e to the x, this is what you get. You get a horizontal asymptote of 0, and then it comes up, and it goes like that. And then 1 plus x is the same as x plus 1. So you take an X line and you just shift it up one, and you get a 45-degree angle like that. So we want to know about the end behavior, describe the end behavior. F is kind of hard to describe, but you should be able to describe all the rest of them. Okay, now if we use the calculator, if we hit second graph to get up the table of values, and we look at function G, as you get very large values, so you had to be like around 100,000, and you all know how to hit second window and then go down to the table and change it to like 50,000 or some large number, and then hit second graph and then go back. So at very large numbers, G starts to go approach 2.718, which is close to E. So G at very large numbers is an approximation, but at very small numbers is not. So we'll do to notice about the relationship between H and K for very small positive values of X. So for very small values, we're talking about like 10 thousandths, 100 thousandths, and small numbers like that, maybe 10 thousandths. You will see that the H and K, the numbers are very, very small. And what you had to do, it says second window, and I showed you this in another video. You want delta table. Once you get to the screen, the second one down is delta table. Put these values in, and then go back and hit second, and then graph to read the table of values, and see what's going on.